This video is over section 7.4, vectors. Here are all of the objectives for this section, and basically this topic comes into play when dealing with physics and the mathematical quantities used to describe motion of an object, for example, is divided into two quantities, scalars and vectors, and that's what we are going to learn about in this section. Now, there's going to be a lot of information we need to cover before we get into some examples. One thing I need to explain to you are scalars. And scalars are basically the quantities that are described by a single value, which we'll often refer to as a magnitude. Vectors, on the other hand, are the quantities that are described by both magnitude, which is like a length, and direction. So for example, the speed of an object is the scalar quantity, but the velocity is the vector quantity, because velocity measures not only how fast an object travels, but the direction also, depending on if the velocity is positive or negative. So the first thing we'll talk about is how to interpret vectors geometrically. And basically a vector in a plane is a line segment with a specific direction. So we will often put an arrow on top to show that it's a vector. The initial point, which we will sometimes call the tip, and then the terminal point, which we will call the tail. The magnitude is the length of the segment, and it is denoted in this way. Definition of displacement here, so you can pause this and read through that definition. This image is the same as it was on the previous slide. Now, when we interpret vectors, two vectors are equal if they have the same magnitude and the same direction. So if we're looking at this vector AB here, then all of these vectors are considered equal because they are the same length and the same direction. So same magnitude, same direction. But the initial point can vary. Typically, when we state vectors, typically instead of writing the initial point and the terminal point like I have circled here, that's not typically how we represent vectors. Typically we use boldface, but if we are writing it, we can't really write in bold, so we will put an arrow on top of the lowercase letter. So they're boldface lowercase letters. Okay, so here we go with our first example. What we want to do is we want to plot these two, okay, so this is the first example, and then this is the second, okay? So what we want to do is we want to graph these vectors and determine if they are equal or not. Remember, in order for two vectors to be equal, we need to have the same magnitude, which is the length, and the same direction. The location of the vector doesn't matter. Okay, so let's go ahead and graph vector V. Because vector V says from negative 3.1, I'm sorry, negative 3, 1, that's here, to 1, 4, that means the vector starts here and ends here. So this is vector V. Then vector W is from 0, negative 3, which is here, to 4, 0, which is here. So this vector is W. And looking at this, these vectors do have the same magnitude. You can, check the rise over run. So rise, run, rise, run, and see that they have the same magnitude and same direction. So yes, these two are equal. Let's do the same thing for the next set. From -4, -2, which is here, to -1, -4. So this is vector A. And then 4, 2 is here, 2, 1, 4, which is here. I can tell right away that these are not equal because they head in different directions. So no, because wrong direction. Okay. Let's try this. So in this example, we are given the starting and ending points of two vectors, vector v and vector w, and we want to find the magnitude of each of them and identify whether or not the two vectors are equal. So if I want to find the magnitude is basically the distance formula. And hopefully you remember that from your previous classes. But the magnitude is denoted with this notation. Sometimes people draw a bar or an arrow over that. But the distance formula says y2 minus y1 squared plus x2 minus x1 squared. So this gives me the square root of 25, which reduces to 5. So the magnitude or the length of this vector is 5. We'll do the same thing with vector w. So applying the distance formula in order to find the magnitude, we have -1 minus 3 squared plus -5 minus a -2 squared. Be careful with that double negative. This also becomes the square root of 25, which is 5. So we have found that both of these magnitudes are 5. Now, in part B, we have to determine if they are equal. Well, remember, in order for two vectors to be equal, not only do they have to have the same magnitude, but they also have to go in the same direction. So you can go ahead and plot these. The first one starts at 0, 0, and then goes to 4. And then the second one starts at -2, 3, and goes to -5. Oops, 1, 2, 3. -5, -1, which is here. So yes, they are the same length or have the same magnitude, but they go in opposite directions. So no, they are not equal. So here we have a couple different vectors. We have vector v and we have vector w. And sometimes we will want to find the displacement between this point and this point, which is represented as v plus w. V plus w is formed by placing a new vector tip to tail. So what that means is we place the initial point of this vector to the tail or the end of this vector. So tip to tail. It ends up being the diagonal of a parallelogram. So what we could do is, if we know this is vector W, we can do another vector W. And then if we know this is vector V, we can do another vector V, and it ends up being the diagonal of the parallelogram. One thing to make sure you know is that if we have a vector V, then negative V represents the same vector but the opposite direction. So if this is vector V, then this is negative V. Sometimes we want to find the difference of vectors, and if we want to find the difference of vectors, basically it's the diagonal again, but the way we find that diagonal is tip to tip. So you can see that here. Tip to tip will give you the difference. And there are a couple ways you can view this. V minus W is the same thing as V plus the opposite of W. So we know that W goes, if this is vector W, then this is negative W. So that's one way to think of it. Sometimes we will have a scalar multiple, and that's just multiplying the vector by some number. And basically, if this is vector V, then 2V is twice the length of V. A half V is half the length of V. And then if we have negatives in front, that just changes the direction of the vector. The 0 vector basically has a magnitude of 0, so a length of 0, and it has no direction. So it's basically an initial point at the origin. Okay, so here we can go ahead and sketch U plus V, and it tells us specifically how we want to sketch this. It says place the initial of U at the terminal of V. So what I'm going to do is I'm going to take this vector and I'm just going to move it over here. So what we can do is kind of look at this as rise over run. So here I will go down 3 units to the right, 3 units. So over here, I'm going to draw it in red. I'll go from here, I go down 3 units to the right 3 units. This will be my terminal point, which is here. So this is U. So now, if I want to find this sum, I'm going to think of this as tip. The tip in this case is here, and the tail is here. So this here will represent the sum of these two vectors. Okay, so this one here, now we want to sketch V minus W. And we are going to do this by drawing V and W with the same initial point. So what I'm going to do is I'm going to take vector W and I'm going to move it up here so that it shares the same initial point with V. So same thing as before. Here I'm going to go down 4 units to the right 2 units. So from here, down 4 to the right 2. So, oops, I'm way off. So this will become vector W. Okay, so If I want to sketch V minus W, V minus W is tail to tail. So in this case, it's going to point to vector V, and this will be V minus W. Okay, here we just have some scalar multiples, and it looks like V should be going in the opposite direction because we have a negative here. So let's start here. It says it's going to start in the standard position. The standard position is the origin. So both of these will have an initial point right at the origin. So if I want to do 2V, I can see that vector V, the starting point to the end point, we will go down 3 units, to the left 2 units. So basically what that means is I need to multiply each of these by 2, and it needs to change direction. So instead of pointing downward, it's going to end up pointing upward. So from here, I'm going to go up 6 units and to the right 4 units. So this here will give me negative 2V. All right, now let's do 3W. Same thing. Here I go right 2, up 2. So my multiple is 3, so I multiply each of these by 3. So I'm going to start here. I'm going to go up 6 units, to the right 6 units. So this will be my terminal point. This gives me 3W. Now we're getting to the meat of this section, the things that I think are more commonly seen and more widely used. Oftentimes we will want to represent vectors in component form. And representing vectors in component form looks something like this. It's important to know that vector notation is not the same thing as point notation. But if you're given the initial point and the terminal point of a vector, it can be represented by taking the difference of the x values and the difference of the y values to get that vector notation. So it's pretty straightforward. So if this is my initial point, so this will be x1 and y1, and the terminal point is this, x2, y2, then if I want to find the component form of vector v, it will be -1 minus 3, comma, 3 minus 8, which is -4, comma, -5. Done. That's it. Not so bad, right? Okay, let's do another one. So here, this is the initial point, and this is the terminal point. So if I want to write component form of this vector, it will be -20 minus 12, comma, 10 minus a -10. This gives me a -32 and 20. All right, so it says if, here's the next part of this question, if v is placed with the initial point here, what is the terminal point of v? Okay, well, basically this tells us our horizontal component, and this tells us our vertical component. So what I need to do is subtract 32 from x and add 20 to 3. So it will become, now we want a point, so this is not a vector, so we'll take 5 minus 32, and we'll take 3 plus 20, to get a negative 27, 23. That's it. A couple things here. I'm not sure. Okay, there we go. Okay, so if I want to identify if two vectors are equal if and only if their horizontal components and vertical components are equal. Basically, all the operations are pretty straightforward. Addition, you add the x values and the y values. Subtraction, same thing. Scalar multiple, everything gets multiplied by that scalar. So nothing crazy or out of the ordinary. Here, oh wow. Okay, here we have some different properties. You can go ahead and pause this and take a look at the different properties, but they're pretty straightforward, nothing crazy. So here I'm given these two vectors, r and s, and I want to add those together. So in this first example, what I'll do is I will add the horizontal components and add the vertical components to get 3, negative 1. Similarly, in the next example, I'm going to subtract. So I'm going to take s minus r and then s minus r. So the new horizontal component becomes 1 and the vertical component becomes 7. In this example, I have a scalar multiple of negative 4, and I want to multiply that by a vector s. So what I'm going to do is I'm simply going to take negative 4 and I'm going to multiply it by this vector. So I end up with negative 8, negative 12. Okay, now this one's kind of putting everything together. So I'm going to take 3 times vector r, and I'm going to add that to 2 times vector s. So this becomes 3, negative 12, plus 4, 6. And then when I add these, I'm going to add the x values and add the y values to get 7, negative 6. And that's it. Not so bad. All right, so sometimes we are interested in the unit vector. And a unit vector is just a regular vector, but it has a magnitude of 1. So its length is 1. If I want to compute the magnitude or find the magnitude, if this is A and this is B, then the same way that we did it before, it's just using different variables. So this was X, this is Y, same thing. Now, sometimes we want to find a unit vector in the direction of a given vector. So if that is the case, so if vector V if we want to give this vector in the direction of V, I will use this here. So basically it becomes the same vector divided by the magnitude of whichever vector we are interested in the direction of. So that's kind of confusing. So let's look at an example to really hammer this in. Okay, so it says find a unit vector in the direction of this vector W and then verify that it's a unit vector. So remember, to verify if it's a unit vector, we want the magnitude to be equal to 1. Okay, so first what we need to do is we need to find this unit vector. And the formula that we will use to find this is going to be A over the magnitude of W and then B over the magnitude of W. So the first thing we ought to do is find the magnitude of this. Okay, so we've done this before. We're going to take the square root of A squared plus B squared, or X and Y. This is equal to 64 plus 225. If I find the sum and take the square root of that, I get 17. So the unit vector W is equal to A over 17, which is negative 8 over 17, and B over 17, which is this. Okay, so here's part of the answer. But now we want to verify that this is in fact a unit vector. So what we want to do is find the magnitude of this new vector and make sure it's equal to 1. Okay, so yeah, it's fractions, it's a little messy, but we're smart and we're capable. So if I want to find the magnitude of this, I'm going to take the square root of negative 8 over 17 squared plus 15 over 17 squared. This gives me the square root of 64 over 289 plus 225 over 289. Keep the denominator of 289. 64 plus 25 is 289. This is the square root of 1, which is equal to 1. Yes, we have found that this is a unit vector. Go ahead and pause this and find the unit vector here in the direction of vector v. Okay, so in order to do this, what we need to do is we need to find A over the magnitude of v and B over the magnitude of v. So first things first is we need to find the magnitude of v. So I do that by finding the square root of the horizontal component plus the vertical component. Each of those are squared. This gives me 25 plus 1, which is the square root of 26. Okay, so then the unit vector v is equal to A, which is 5, over root 26, and B, which is negative 1 over root 26. You can go ahead and rationalize the denominator if you want, or leave it as is. So you'll find that there are different ways to represent vectors. We've seen lots of different ways so far. Another way in which we can represent vectors are in terms of I and j. I represents this vector and j represents this vector as shown here. And they're basically the unit vectors in the direction of the positive x and y axes. So if we have vector v that is represented here, if it says represent this vector in terms of I and j, then vector v becomes this. So all we do is we take A, attach it to I, take B, attach it to the j. So, and again, this is just the scalar horizontal and vertical components. So if this is our vector and we want to write it in terms of ij, all we do is we take this, attach it to I, and then take this, so plus, or in this case minus 30, and attach it to j. So this is the vector written in terms of I and j. Now I want to make a special note that vector I is not the same thing as the imaginary I. They are two different things. Sometimes we will want to identify the direction angle of a vector, and it's the same as all the angles that we've dealt with before, which is shown here on this slide. So again, initial side, this will be angle theta. Typically, we represent theta in terms of degrees between 0 and 360. So, let's see. Here, so this is basically introducing the direction of a vector. We already know how to find the magnitude. But if I want to find the direction of a vector, this is the formula I use. It comes from this triangle here, SOHCAHTOA, and basically it ends up, if I apply SOHCAHTOA to this, I can get A by itself and B by itself, and it will be these results here. So A is equal to the magnitude of the vector times cosine of the direction angle, and B is the magnitude of the vector times sine of theta. So these are referred to as the horizontal and the vertical scalar components. There are a couple other ways that it can be shown, which is here. So basically vector V written in this way, A is this, B is this. You can also write it in terms of I and J. So this was A and this was B, so you just attach it to the I and the J. Nothing crazy. You're welcome to pause the video and kind of analyze this a little bit to get a better foundation if needed. Okay, so here I think it just makes more sense with an example. So it says write the vector V in the form of I and J, where the magnitude is given to us. That's really nice, and the direction angle is given to us. So what we need to do is we need to find A and we need to find B. Remember, A is the magnitude of V times cosine of theta, where B is the magnitude of V times sine of theta. So let's go ahead and find A first. The magnitude of V is given to us, which was very kind. It's 10 times cosine of theta. The direction angle is also given to us as 3 pi over 4. All I need to do is simplify this, and I have A. So here comes the unit circle again. So 3 pi over 4 is almost 4 pi over 4, which means it's in the second quadrant. So we have root 2 over 2, root 2 over 2. In the second quadrant, cosine is negative. So this ends up becoming 10 times negative root 2 over 2. I can put the 10 over 1, multiply across the top, across the bottom to get negative 5 root 2. This is A. Now I'm going to find B. B is the magnitude of vector V, which is 10, times sine, this time, of 3 pi over 4. We've already found sine of 3 pi over 4, so I'll take 10 times root 2 over 2, which reduces to 5 root 2. And this is B. So if I want to write the vector V in the form of I plus J, it will become negative 5 root 2 I plus 5 root 2 J. That's it. Okay, now this example is a little more complicated because now we are not given the magnitude and the direction angle, and we need to find each of those. So if I want to find the magnitude, that's something we've been doing lots. Remember, the magnitude of S in this case will be the square root of a squared plus b squared. The direction angle will be found by taking tangent of theta is equal to b divided by a. And then we'll take tan inverse of both sides to find that theta. Okay. When we find the direction angle, note that it needs to be an angle between 0 and 360. So we don't want any negative angles. Also note that it should be in degrees. So let's first find the magnitude of vector s. So in this case, I'm going to take a squared plus b squared. This is equal to 49 plus 9 under the radical, which is 58 under the radical. Great. Okay, now to find the direction angle, we'll take tangent of theta is equal to b, which is -3, over a, which is 7. So if I take tan inverse of both sides, I find that theta is tan inverse of -3/7. So in my calculator, I'm going to make sure it's in degree mode, and this gives me approximately -23.2 degrees. Now, this is a problem because this angle is in quadrant 4. Since it's negative, remember we're going to go in the opposite direction. But we need it to be in between 0 and 360. So this negative angle is kind of like our reference angle. So to find our actual angle theta, we are going to take 360, which is a full revolution, minus this angle here. So we will find that theta is 336.8 degrees. So now we're going to get into the applications of this. And again, vectors come into play a lot in physics. So if you're interested in physics or have to take that class, you'll learn more about them there. But this first example talks about a baseball being thrown with a speed of 65 miles per hour. That is the magnitude. And then it also tells us that it's at an angle of 12, which is going to be our the angle that we are going to be used. So that's the direction angle here. So it says write the velocity vector v at the time of release in terms of I and j and round the components to the nearest tenth of a mile per hour. So basically what's happening is this ball is being thrown at this angle of 12 degrees. Velocity is 65. Theta is 12 degrees. Okay, so not velocity magnitude, I apologize. So if I want to write this vector in terms of I and j, what I want to find is this. So remember that a is found by taking the magnitude of the vector times cosine of theta. And we know each of these here. So 65 miles per hour times cosine of 12 degrees. So you'll want to be in degree mode. Plug this into your calculator and you will find that this is 63.6. Then B is the magnitude of V times sine of theta. So 65 times sine of 12 degrees, plugging that into your calculator, you should get approximately 13.5. So you know A, you know B, so you can find this. The velocity vector V at the time of release will be 63.6 I plus 13.5 J. And again, this is the horizontal component and the vertical component. In this example, we have 3 different forces, and they're represented by F sub 1, F sub 2, and F sub 3. And they're acting on this object. So basically, all of these forces are pushing or pulling this object, and we want to find the resultant force. This is found by taking the sum of all the forces. So what I will do to find this, the resultant force, is F1 plus F2 plus F3, which is equal to, and then we're just going to add all of these. So F1 is 10I minus 3J plus negative 2I plus J plus 11I. If you want to say plus 0J, you certainly can. And these should probably be written as vectors. So all I'm going to do is add the horizontal components. So that gives me 19I, and then the vertical, which gives me minus 2J. So that's the resultant force, R. Now in part B, it says, what additional force is needed for the object to be in static equilibrium? Well, static equilibrium is when the resultant force, or when R, is equal to 0. So the forces basically need to counteract one another. So if I need to find another force that can be added to this force, what would I need to add to this to get a result of 0? Well, basically it's the opposite of everything. So the additional force would be the opposite of I and the opposite of J, or A and B rather. Okay, so that's that. Take a moment and pause the video and see if you can do this example. So in this example, a man is exerting a force of 80 pounds on an object. So if somebody is exerting a force, that's the magnitude. So we know that F, the magnitude of F is 80. And it also gives us the direction angle. So theta is 30 degrees. And we want to write the force vector in terms of I and J. So we want to find this. So F cosine of theta I plus magnitude of F sine of theta J. Okay, so we already know anytime you're given a force, that is the magnitude. So this becomes 80 cosine of 30 degrees times vector I plus 80 times sine of 30 degrees times vector J. Let's see, 30 degrees has the corresponding ordered pair. So this is like pi over 6. So root 3 over 2, 1/2. This is in quadrant 1, so both sine and cosine are positive. So this becomes 80 times root 3 over 2 times vector I plus 80 times 1/2 times vector J. Multiplying this out, you get a final answer of 40 root 3I plus 40J. And that is the final force vector in terms of I and J. And this concludes section 7-4.